I'd like to welcome Professor Mariya Moosajee, Professor of Molecular Ophthalmology at University College London and consultant ophthalmologist at Moorfields Eye Hospital, specializing in genetic eye disease. Today we'll be talking about the potential for gene therapy in vision loss in Usher patients. Welcome, Mariya, in the first place.
Thank you so much, Noor.
So, as a consultant ophthalmologist, you see Usher syndrome patients with varying degrees of vision loss, don't you?
Absolutely. So in my clinical practice, I see children and adults with Usher syndrome. Now, there are three types of Usher syndrome, type 1, 2, and 3. And that gives us an indication of the types of and patterns of sight loss they'll develop. So individuals with type 1 are often more severely affected, and children will present with vision problems, mainly difficulties with their night vision, around the age of kind of 5 to 6. That will go on to then cause a constriction of their visual fields. And then in adulthood, their central vision can be affected also, leading to sight loss. With type 2, it's slightly milder. So adolescents present with the night blindness and then follow the same pattern. And patients with type 3 have a more variable presentation. So it can be slightly later or earlier.
I see. And now there's an emerging technology called gene therapy. How could all these patients benefit from gene therapy?
So gene therapy is revolutionary for our field. It involves replacing a healthy copy of the gene back into the retina cells. The difficulty with Usher's syndrome, there are several genes that cause it, and the genes are very large in size. So conventional gene therapy utilizes viruses to package a healthy copy of the gene to deliver it to the retina. But those viruses can only hold genes that are of a certain size. So less than, say, 4 to 5,000 letters, genetic letters in size. The Usher genes, and in particular, say, USH2A, which is the commonest gene to cause Usher syndrome and the commonest cause of type 2 Ushers, is about 16,000 letters in size.
Way larger. Yeah.
Well, it's 4 times larger than the carrying capacity of these viruses. So we can't therefore use them. So we need to think about different approaches for delivering this gene back to the retina. And that's what my group's doing. We are developing a non-viral gene therapy.
Yeah, because what alternatives are there to viral delivery of the desired genes?
Yeah. So in my team, what we have done is we have developed a circular piece of DNA, and we have inserted the entire copy of the USH2A gene into that. So it accommodates the full 16,000 letters.
That already checks the first box.
So tick, we are able to create some sort of delivery vector. And the great thing about these circular pieces of DNA is that it can hold a gene of any size. So it would be applicable to all of the Usher genes. So we've developed this vector and we've delivered it to different disease models. So we have a zebrafish that has Usher syndrome in our lab that we created using gene editing. And we have patient cells kindly donated by individuals with Usher syndrome that have the genetic defect. And we're able to use the patient cells and grow them into small retinas in a dish.
Yeah, because we've now established that you can fit the entire gene as a circular piece of DNA.
Yes.
But how do you still bring that circular piece of DNA into the cell, I wonder?
So for those cell and zebrafish models, we can inject directly into the cell. And that's fine. And what we've seen is then once the vector is within the cell, it is producing the healthy copy of the gene and the normal protein, and it's actually restoring the function within those disease models. But how do we then translate that to our patients? So this is the next stage of our work. The reason that viruses are so good for gene therapy is because they can infect a cell. we all know that because we get the common cold, because we get an infection from a virus. So viruses have that capability. These circular pieces of DNA don't have that capability. They cannot infect a cell. So we need to find some sort of vehicle that we can place these the DNA in, and it will help it to enter into the cells. And so we've been working with collaborators at UCL to look at something called lipid nanoparticles.
What are they?
This is basically like a solution of a mixture of lipids, so fats and proteins. And if I can give you the analogy of, for example, you've got oil and water. You know they don't mix. So how can we get the oil to mix with the water? We can add soap. And we know, like, for example, if we've got oil on our hands, if we add soap, it dissolves the oil nicely, and then we can wash it away with the water.
Yeah, so you've developed kind of molecular soap.
So it's like exactly like a molecular soap that can package our DNA vectors, and once it touches the surface of the cells, it can help it to enter into them.
Wow.
And so we've got some really nice lipid nanoparticles now. We've been injecting them into the mouse retina and into a rabbit model of Usher syndrome with a collaborator in the University of Michigan, Dr. Dongshan Yang. And we're seeing really nice expression of our genes in the photoreceptor cells, the light-sensitive cells at the back of the eye. So we're really excited. We still have a lot of work to do. We want to look at how long our genes are able to produce healthy copy of the protein once we get them into the cells, and we want to make sure that this molecular soap is safe and it's not causing any sort of toxicity. So we still got a bit of work to do, but we are really heartened by the progress we're making, and we're looking forward to the future.
Yeah, well, me too. And if I want to kind of sketch a timeline, when would you think this would become available also for Usher patients? Is it a couple of more years, maybe decades? How do you picture that?
Yeah, so I mean, at the moment, I would like to thank the Ushersyndroom Society, because they funded us with their Moon Rocket grant to do the work on the rabbits. I'd also like to thank Cure Usher. They're our two big funders of this work. It really does depend on funding. We can get the kind of preclinical work to a certain stage, but really when you're then thinking about moving to clinical trials, you're looking at a lot more funding. We're talking about millions. So, I mean, I would like to say within the next decade, funding dependent. And then, let's see.
Maybe it's a good opportunity to stress once more how promising and innovative this technology is.
This is, I mean, honestly, if this works, it will be applicable to not only all the Usher genes, but to all the other genes, whether it's large or small. And there are benefits over viral vectors. We know, for example, we have one approved retinal gene therapy available in the world, and it's vorretigene neparvovec, or Luxturna. And there, patients who receive this, there's 50% risk of having an ocular adverse event, in inflammation, infection. Sometimes even the retina can wear away. And it's thought to be down to a subacute viral response. And so if we can move away from viruses, this might be much more safer and more effective. I encourage people to go out, raise funds, watch this space. But it has the promise of helping a lot of inherited retinal diseases, not just Ushers.
And so for now, if you focus on the lipid nanoparticles, the molecular soap you told me, how does this research contribute to the Usher Foundation's moonshot goal of making diagnosis and treatment for Usher syndrome patients standard of care worldwide?
Yeah, so I would say the work that we're doing from both a clinical and a research perspective really focuses on those two goals. So from a clinical perspective, early genetic testing is paramount. I'm very lucky in the UK, in London. I can offer every patient whole genome sequencing as part of their routine clinical care. So there's equity of care. Anyone can get get access to that. It means we get a fast and accurate diagnosis. That helps the patient then be plugged into the right clinical services earlier, where we can minimize comorbidities. We can also get them in touch with the researchers that are working on their condition directly, and also offer them access to clinical trials.
It's a collaborative effort.
So it's amazing.
Yeah.
And then from the research perspective, developing this non-viral gene therapy directly works towards really giving everyone with Usher's the chance to access a treatment, because some of the treatments that are being developed may be mutation specific. So only a certain proportion of patients can access that. For example, with the Ultevursen trial, patients only with exon 13 mutations can access that. But there are a vast number of patients who have mutations outside of that coding region.
So this might provide therapy for more Usher patients.
Yeah, this will help everyone.
Sounds very exciting, Mariya.
Yeah, very
exciting.
Thank you so much. Thank you very much, Noor.